Okay, so welcome everybody to this special seminar. So our speaker is Diego Fuentes. So Diego is currently an applied math instructor at MIT. Before he got his PhD also from MIT in 2018, supervised by Pablo Barillo. And he also spent, before he moved back to MIT, he actually spent 8 months or so at the Max Planck Institute in Leipzig in Germany. And before joining MIT to do a master's and a PhD there, he did his undergrad degrees in Bogota in Colombia. So welcome, Diego, and please go ahead. We're happy to have you.
Thank you very much for the introduction. I'm very happy to be able to talk here. The title of this talk is going to be Advancing Scalable Provable Optimization Methods in Semidefinite and Polynomial Programs. And if there's something that you may notice in the title is that this talk is going to be about optimization. So let me just start simply by mentioning that optimization is actually a very broad field that has applications in many, many areas in science and engineering. And in this slide, I have a sample of 9 problems from science and engineering where optimization is used. So let me mention these concrete applications. So for instance, optimization is used in problems from machine learning, such as tensor principal component analysis or matrix completion. It's also used in problems from robotics, such as rotation synchronization, or in the analysis of the kinematics of a robot. It's used in the analysis of power systems or in the analysis of chemical reactions. And we can also use it to understand some quantum computer architectures. And we can also use it for phase retrieval, which is a problem that appears in crystallography. And finally, we can also apply it for classical problems from computer science, such as the Max-Cut problem. So as you may see in this slide, the range of applications of optimization is actually quite broad. My research centers around the development and analysis of optimization methods that satisfy two key properties. One of these properties is that I want to develop methods that are scalable so that they can handle real applications. And this is something that is particularly important nowadays because, well, we are living in a world where everything has big data and the size of the problems just keeps increasing. And then another key property that my research also pays quite a lot of attention is in developing methods that have provable mathematical guarantees. What do I mean by that? So what I mean is that I want to design a method for which we understand when and why is it that it works. And if we understand these questions, then we might also be able to understand when is it that a method is going to fail, which is very important from the application point of view. So this is my broad goal, the broad goal of my research. And in order to achieve this goal, I actually make use of several tools from pure and applied mathematics. For instance, I used quite a lot algebra, combinatorics, geometry, and variational analysis. What I'm going to do in this talk is that I want to mention to you how is it that my past research has approached this goal, particularly in the context of 2 classes of optimization problems that are called semidefinite programs and also polynomial programs. So the remaining part of this talk is going to be divided into 2 parts. The first part is going to be about semidefinite programs, and the second part is going to be about polynomial programs. Let me proceed to the first part of the talk, which is about semidefinite programs, which we're going to abbreviate as SDP. Semidefinite programs, or SDPs, are a very, very well-behaved class of optimization problems. They are extremely well-behaved. And they actually appear in many applications in science and engineering, such as the ones that you may see on this slide. For instance, rotation synchronization or tensor principal component analysis. If you have heard before of linear programming, it turns out that semidefinite programming is actually quite similar. In linear programming, our goal is to minimize a linear function on a set which is defined by the intersection of a linear space with the set of non-negative vectors. And this intersection may look like the triangle that we have on this slide, but more generally, it's going to be a polyhedron. In semi-definite programming, actually, the situation is very similar. We are again minimizing a linear function, except that now the set is defined by the intersection of a linear subspace with the cone of positive semi-definite matrices. And as you may notice in this slide, this cone actually has some curvature. It now has some curvature, and because of that, that means that the intersection is now going to be something more general than a polyhedron. But importantly, both linear programs and semi-definite program share many interesting properties. And in particular, both of them are convex optimization problems, and we can solve these problems in polynomial time by using very similar techniques, in particular by using interior point methods. Let me illustrate how is it that semi-definite program appear in applications. And I'm going to motivate that by means of a concrete example. So I'm going to consider the case of rotation synchronization. In this problem, we have some objects that are located in 3D space. For instance, we may assume that they are, for instance, drones. And what we want to do is to find the orientation of these objects. And the information that we are given is an estimate of the relative orientation among some of these pairs. So given these noisy estimates of these relative orientations, we want to find the global orientations for each of the objects. This problem has applications in particular in robotics, but also in areas such as computer graphics and cryo-electron microscopy. And one technique that has been actually very successful for this type of problems is a technique that I'm going to call the relaxation strategy. And the idea of this strategy is the following. The first part is simply to model this problem as an optimization problem. And here in the top, you have an optimization problem. So this is an optimization problem where the variables are actually the rotations that I'm trying to find. And we minimize a function, and this function that we are minimizing is somehow trying to tell us that the rotations that we are finding should be consistent with the estimates that we are given. So now we have an optimization problem, but there is one important issue, which is that this optimization problem is actually quite complicated. In particular, it's a non-convex optimization problem, and it's also NP-hard. Consequently, the main idea of this relaxation strategy is to approximate this problem that is very hard with a simpler one. And the simpler optimization problem is going to be a semi-definite program, or an SDP. And as I mentioned before, SDPs are very well-behaved class of problems. In particular, they are convex and they are tractable. We can solve them in polynomial time. Once we have this approximation, we can solve this approximation. This is the semi-definite program. We solve the semi-definite program. And there's one final step, which is that at the end, we have to retrieve the solution of the original problem from the solution of the SDP. So remember that the solution that we care about is the rotations themselves. So then at the end, once we solve the semi-definite program, we want to retrieve the rotations. So this strategy, it turns out that has been successful not only for this rotation synchronization problem, but also for many, many other problems. Particularly, it has been successful in many estimation problems. What do I mean by an estimation problem? So what I mean is that we have a parametric statistical model. It depends on a parameter. And what we want to do is to estimate the parameter that best explains some observations from this model. And there are many examples of this type of estimation problems, for instance, rotation synchronization, but also tensor principal component analysis, phase retrieval, noisy matrix completion, and many other problems. And in all of these problems, this relaxation strategy has been quite successful. What do we do? Well, we do a similar procedure as before. First, we formulate the problem as an optimization problem. But as before, this problem is often complicated. It's often non-convex and NP-hard to solve. Once we have this non-convex problem, we then approximate it by using a simpler problem, which is going to be the semi-definite program. Then we solve the semi-definite program and we're going to obtain some solution. And the final step is to use the solution to retrieve the solution of the original problem. So that's the relaxation strategy, and it has been successful in many practical applications, but there are some important challenges for this relaxation strategy. In particular, one very important challenge is that it's actually not clear when is it that this relaxation strategy is going to work well. Particularly the last step, once I solve this convex relaxation, this SDP relaxation, is not clear if we can obtain the solution to the original problem. That's one step that is not clear at all. So one important issue is to provide provable guarantees of when is it that this relaxation strategy is going to work well. Another important challenge is scalability. In this strategy, the main bottleneck, the main computational bottleneck is typically solving the semidefinite programs. I mentioned before that semidefinite programs can be solved in polynomial time, in particular by using interior point methods. However, these type of techniques do not behave well for large-scale problems. In particular, they often run out of memory. My past research has tried to tackle this scalability issue, but taking advantage of problem structure, in particular by taking advantage of geometric structure in order to derive more efficient relaxations that can be solved more efficiently. An alternative and also complementary way to tackle this scalability issue is to develop new techniques that don't suffer these memory issues that we have for interior point methods. And this is something that has been done by many other researchers. And in particular, there's one class of methods that has been increasingly more used for solving large-scale semidefinite programs. And this is the Burer-Monteiro method. This is one of the most widely used methods nowadays for solving large-scale semidefinite programs. But although the fact that this method it's very well used in practice, we still don't understand very well why is it that it works. And until last year, there was one very important open problem, which was to understand the computational complexity of this method. So in this slide, I have 3 concrete challenges in which I have worked on. For the purpose of this talk, I don't have time to go over each of them. So what I'm going to do is that I'm going to briefly talk about our results in this first point regarding when is it that the relaxation works. And then I'm going to spend a little bit more time about the complexity of this Burer-Monteiro method. Let me proceed about to the first topic, which was when is it that this relaxation is going to provably work. In joint work with Parrillo, Agarwal, and Thomas, we developed a general theory that allows us to understand when is it that SDP relaxations are going to behave well, particularly in the setting of estimation problems. And what we showed is that there are many important estimation problems from applications that actually can be solved exactly by means of semidefinite relaxation, particularly in the low noise regime. And this theory can be applied to many problems. For instance, it can be applied to the rotation synchronization problem, to the tensor principal component analysis problem, but also to many other applications that you may see here on the left-hand side, and that cover areas from robotics, computer vision, machine learning, control, and symbolic computation. Let me proceed to the last challenge that I mentioned in the slide, which was about the complexity of this Burer-Monteiro method. As I mentioned before, the Burer-Monteiro method is one of the most widely used methods nowadays for solving large-scale semidefinite programs. And the basic idea of this method is actually extremely simple. In a semidefinite program, we have a problem such as the one that I have on the top. For us, the important part now is that the optimization variable, it's a matrix X. That's the variable over which we are optimizing. This is a matrix, it's a symmetric matrix that it's furthermore positive semidefinite. Let's assume that this matrix has dimensions n times n. Because this matrix is positive semidefinite, it's possible for us to factorize it in the form y times y transpose. And as you may see in this diagram, I'm going to assume that the number of columns of y, which I'm denoting p, it's much smaller than the number of rows, which I'm calling n. The main idea of the Burer-Monteiro method is to rephrase the optimization problem that I have on the top in terms of this matrix, of this new matrix Y, and to solve the new problem in terms of y by using local optimization. And there is one clear advantage, one immediate advantage that we gain by doing so, which is a reduction in the memory usage. Because instead of having to store n times n entries for the matrix X, now we only have to store n times p entries for the matrix Y. And remember that memory was one of the limitations, particularly for interior point methods. So by this very simple idea, we can gain significant improvements, at least directly in terms of memory. However, there is also one important disadvantage, which is that convexity is lost. I mentioned before that semi-definite programs are very well-behaved classes of optimization problems, in particular because they are convex. But once I rephrase the problem in terms of this matrix Y, it turns out that convexity is lost. And if convexity is lost, that means that we have to start to worry about problems that we didn't have to care about before. For instance, we have to worry about whether we are going to converge to a local or to a global minima. This Burer-Monteiro method was introduced around 20 years ago. And since then, many researchers have tried to understand why is it that this technique works well. And in particular, they have tried to explain what is the behavior of this method. And because of this work, we now understand this method a little bit better. And we understand that there are two important regimes regarding the parameter P. And remember that P is the number of columns of the matrix Y. The first regime is that the parameter P it's small, particularly smaller than square root of 2 times m, where m is the number of constraints. And in this regime, there's really not much that can be done. It's known that the geometry of the optimization problem is very bad. And in general, there's not much that we can prove in this regime. But if the parameter P surpasses this threshold of a square root of 2 times m, then the situation is a lot nicer, at least from the geometric point of view. And under suitable assumptions, there's going to be no spurious local minima. But despite the fact that we understand the existence, that we know the existence of these two regimes, and consequently we understand better the behavior of this method, until last year, it was still unknown what was the computational complexity of this method. We have known for a while that SDPs can be solved in polynomial time by using, for instance, interior point methods. But until last year, it was still unknown whether the same can be achieved by using this more recent class of techniques. In joint work with Burer-Monteiro, we showed that if the parameter P is slightly above the bound from above, so notice that I have this additional factor of plus epsilon, if we go above this bound from above by an epsilon amount, then we can show that this Burer-Monteiro method is going to probably solve the semi-definite program in polynomial time. More precisely, we showed this theorem that I have here. I don't want to go into the details of this theorem, but perhaps let me just emphasize once again that we just need to go slightly above the bound that I had in the previous slide. So in this case, this extra factor of epsilon is an arbitrarily small fixed constant. And under this assumption, we can show that this Burer-Monteiro method is going to behave well and it's going to compute the optimal solution of the SDP in polynomial time. I would like to point out that this bound that I have that you may see in this slide, this bound, it's something that actually we can easily see in practice as well. We need it for the theorem, but it's also easy for us to get examples where we see this bound also in practice. And in particular, in this case, I have a simulation of a certain optimization problem, a certain SDP that I'm solving with this Burer-Monteiro method. And what this graph is showing is that the number of experiments that are solved by the Burer-Monteiro method significantly increases. So we see that there's a very steep jump when we cross this vertical line over here. And this vertical line is precisely the bound of a square root of 2 times m that I mentioned in the previous slide.
Can I ask a question?
Yes.
And this is Alex. Hi, Diego. So maybe I missed something, but is there some assumption here about the semi-definite program? Because what if the solution is actually full rank? of the actual semi-definite program. So you're saying here this is approximately feasible and approximately optimal. So where does the nature of the SDP problem itself and the rank of the actual solution enter here?
So this bound that I have here of a square root of 2 times m, this is something that has been studied for many years in the semi-definite programming literature. And the reason is that this bound tells us the smallest solution, the smallest rank for which we are guaranteed to have an optimal solution. So it's known that there is always going to be a solution of rank is a square root of 2 times m. So at least from the point of view of feasibility, this bound is going to guarantee that there is going to be an optimal solution of this rank. Does this answer your question?
So meaning that this solution is going to be as good as any other solution. Exactly.
Can I also ask a question?
Yes.
So epsilon doesn't appear in your polynomial time. That seems very surprising.
Yes. So the idea is that this epsilon that I have here, it's going to go into the degree of the polynomial. So I have here polynomial time, but the polynomial actually depends in 1 over epsilon. So that's why I want this epsilon to be a fixed constant. The degree of the polynomial depends on the epsilon. Any other question here?
Because I also have a good question. So it seems that the case for P is larger is nicer, right? Can you not, maybe that's a neat question, can you not just add columns to the matrix Y and make them 0 columns to artificially inflate P?
Yes, but you have to make use of all the columns when you're solving the optimization problem.
So you're saying it's more expensive?
Yes, exactly. It's going to be more expensive. So in practice, actually, people very, very rarely go up to this bound because they want to use as less columns as possible.
Okay, thanks.
Okay, let me also point out that this theorem that I have here, this is a complexity theory. But it turns out that the main idea behind this proof, it's actually a geometric idea. And the idea is the following, that this Burer-Monteiro method, what we showed is that the Burer-Monteiro method, it's only going to fail when a certain geometric condition is satisfied. And the geometric condition is that the cost matrix that I'm calling here C has to lie on a certain tube. What do I mean by a tube? I mean precisely what you see here on the left-hand side. I want to be on a tubular neighborhood around a certain algebraic variety. And it turns out that tubes around algebraic varieties or around manifolds have actually quite a rich history in differential geometry and also in algebraic geometry. And for instance, you may see that there's a whole book dedicated around the study of these tubes. So behind this complexity theorem that I have here, actually there's some very nice geometric ideas. Let me move on now to the second part of this talk, which is going to be about problems involving polynomial equations. And these type of problems actually appear also in many applications in science and engineering. Here I have a few of those applications, for instance, power networks or optical quantum computing. Let me illustrate as before, how is it that polynomial equations appear into these problems? And let me start again as before by focusing on a concrete application, on the case of a power network. So let's assume that we have a power network, for instance, the power network of a city or a power network of a country. This network is going to have multiple generators and also multiple loads. And I'm going to consider the following problem. Let's assume that I know how much power was consumed by each of the loads. And in addition, let's also assume that I know how much power it was injected by each of the generators. And given all these consumed and injected powers, our goal is to determine the voltages for each of the nodes of the network. We can model this problem by taking advantage of the theory of circuits, in particular by taking advantage of Kirchhoff equations. And if we made use of this theory, what we will end up with is with the system of equations that I have here. The first row gives us a formula for the active power of a node in terms of the voltages of the adjacent nodes. And the second line gives us a formula for the reactive power of a node in terms of the voltages of the adjacent nodes. Since I am assuming that we know how much power was injected and consumed by each node, then that means that I actually know the left-hand side. I know the value for Pi and for Qi. And the problem in this case is to find the voltages, to find these Vs that satisfy these equations. So as you may notice, the problem of this problem that from power networks that I started with, at the end can be modeled by means of solving a system of polynomial equations. And that's something that is good because solving system of polynomial equations is it's a problem that has been well studied. And there are known techniques for solving this type of problems. However, state-of-the-art techniques, all of them suffer from an scalability issue. Solving system of equations that involve many variables is very hard. Let me also mention how is it that polynomials appear in another type of applications, in this case in optical quantum computing. In an optical quantum computer, there's typically an interferometer. This interferometer consists of multiple optical devices, for instance, mirrors, and we inject some photons to the interferometer. At the end, there's going to be something, and we're going to measure what we obtain just at the end of all these circuits. And I'm going to consider the problem of simulating this quantum device by making use of a classical computer. So we have this quantum device, but I want to understand whether we can simulate it efficiently by using a classical one. Mathematically, if we want to do that, what we need to do is to sample from the probability distribution of the photons that we scatter through this interferometer. And it turns out that this probability distribution actually admits a rather concrete formula. Each of the probabilities is proportional to these fractions that you may see here in the bottom. And the most important part is actually the numerator. This numerator, it's a polynomial function. This is known as the Hafnian. This is a polynomial function in the entries of a matrix. However, this polynomial function is actually a very, very big polynomial because it has one term for each possible permutation of the numbers from 1 up to n. So that means that this polynomial, it's a very long polynomial, and consequently, it might not be that surprising to you that evaluating this polynomial, it's actually very hard. So as before, if we want to simulate this quantum device by using a classical computer, we again have an scalability issue. As in the previous two applications, it turns out that there are many other applications where polynomial equations naturally appear. But it turns out that whenever we are dealing with polynomial equations, typically, scalability is going to be an issue. My work has tried to take advantage of the underlying problem structure in order to develop new techniques that are more scalable. In particular, I have developed new techniques that take advantage of sparsity, of the underlying sparsity structure of the problem. More precisely, I developed new techniques for solving sparse polynomial systems, and also for computing Hafnians and some related polynomials, for instance, permanents of sparse matrices. This plot that you may see here in the right-hand side, it illustrates the performance of a technique that we developed, that is shown here in red. This is a technique that we developed that I'm going to talk to you later. And I'm comparing them against two state-of-the-art techniques. And what you may see in this plot is that our technique scales significantly better than state-of-the-art methods. In particular, in this case, if I have 50 variables, our technique completes the task within 1 minute, whereas state-of-the-art techniques were not able to complete the task within a whole day of computation. As before, I don't have enough time to discuss both of these methods. So what I'm going to do is that I'm going to very briefly talk about our results for Hafnians, and then I'm going to talk in a little bit more detail about our results for solving polynomial systems. So let me talk a little bit about the computation of Hafnians of sparse matrices. In joint work with Barrillo, we developed a new algorithm that takes advantage of sparsity and graphical structure in order to compute these hard polynomials, for instance, Hafnians, much more efficiently. And later, in joint work with collaborators from Xanadu Quantum Technologies, we applied these sparse Havian algorithms to the context of quantum optical computing. And what we showed is that a certain architecture that is known as Gaussian boson sampling can be efficiently simulated by a classical computer if the underlying circuit satisfies two nice properties. In particular, if the underlying circuit is shallow, which means that it doesn't have too many layers, and also if the gates are local, which means that they don't receive too many inputs. Let me move on now to the case of solving sparse polynomial systems. I mentioned before that polynomial systems have many applications, for instance, in power networks. But as I mentioned before, scalability is typically an issue. However, it turns out that problems, that polynomial systems that appear in applications very often have a nice sparsity structure. And the reason behind this sparsity structure is often physical constraints. For instance, in a power network, constraints only involve nodes that are nearby in the network. So physical constraints often lead to a nice sparsity structure. Our goal is to develop new techniques that take advantage of problem structure and in that way are more efficient than state-of-the-art techniques. In order to do so, our first step is actually to model the problem by means of graph. So the idea is the following. I start with a sparse system of equations and I want to construct an associated graph that models the underlying sparsity structure. And what we say is the following. The underlying graph is gonna have as vertices the variables that I'm denoting as x0, x1, ... And for the edges, I'm gonna connect two variables if they appear in the same equation. So here in the bottom, I have an example. So in this case, I have 4 polynomials involving 4 variables, x0, x1, x2, x3, and x3. The underlying graph is going to have 4 variables, which I'm calling 4 vertices, which I'm calling 0, 1, 2, and 3. And each of these edges corresponds to one of the equations. So for instance, this edge that I have here between node 2 and 3, this tells me that the variables x2 and x3 appear in the same equation. Similarly, this edge that I have here, 1 and 2, it tells me that 1 and 2 appear in the same equation, and so on. So the basic idea is that if I have a sparse polynomial system, there's a very simple way in which I can model the underlying sparsity by using a graph. Getting this graph, it's a procedure that is extremely simple. The important question is whether we can efficiently use this graph in order to solve the system of equations. And what we showed is that it is indeed possible. And yes, but it is indeed possible to take advantage of this underlying graphical structure to develop new techniques. But we have to be careful because state-of-the-art techniques are not going to behave well with respect to this graphical structure. And I'm going to motivate this by means of an example. So in this example, I have a relatively simple polynomial system. I have one cubic equation for each I from 1 up to n, and one quadratic equation, again, for each I from 1 up to n. This is a relatively simple system of equations. You may see that these are actually very sparse equations. Each of the equations involve only 1 or 2 variables. And the underlying graph is also very simple. The underlying graph, in this case, is the cycle graph. So in this case, we have a polynomial system. It looks very simple. The underlying graph structure is actually very simple. The intuition is that solving this polynomial system shouldn't be too complicated. But yet, if we try to solve it by using state-of-the-art techniques, for instance, Grobner bases, what we will obtain at the end is quite complicated. So if you haven't heard, Grobner bases is perhaps one of the most widely used methods for solving polynomial systems. And if I try to compute these Grobner bases for this polynomial system, even if I only have 9 variables, even for only 9 variables, the output is going to be actually quite complicated. In this case, we're going to obtain 13 polynomials, and each of these polynomials looks like the one that you see in the bottom. So notice that these are very long, complicated polynomials. These are very dense polynomials. They involve all the variables. Despite the fact that I had such a nice graphical structure at the beginning, the Grobner bases computation destroyed this underlying graph structure. And at the end, I obtained some very dense polynomials. And the biggest problem is that the size of these polynomials, it's actually going to grow exponentially with the number of variables. And consequently, simply writing down the answer from this granular basis computation is going to take exponential time. Simply writing the answer, even if we already know the answer. So what this example tells us is that if we want to take advantage of graphical structure, we need new algorithms. And not only new algorithms, but we also need new data structures. Because as I mentioned before, even if I knew the answer in the previous case, simply writing it down, it will take us exponential space. So what we developed is a new data structure for representing polynomial systems that we call Chordal networks. And this is a graphical data structure. And you may see an example here on this figure. So how should you make sense of this data structure? The idea is to look at the paths in this diagram. So for instance, here I have one path, here I have another path, here I have another path, another path. There are many paths in this diagram. If I increase the number of variables, then the number of layers that we have, it's going to increase. And if we increase the number of layers, the number of paths that we're going to have, it's going to increase very, very rapidly. It's going to grow exponentially. And it turns out that each of these paths is telling me one of the solutions of the polynomial system. So what is happening in this case is that we have a polynomial system that it's actually quite simple, but yet it has an exponential number of solutions. And that's something that often happens. And that's the reason why state-of-the-art techniques do not behave well, because it has too many solutions. What this graphical data structure that we developed allows us to do is to represent this exponentially large solution in a very compact way by making use of these graphs that we have here. More generally, we show that if we start with an arbitrary polynomial system, we can always obtain at the end a Chordal network representation, a data structure, this Chordal network that is going to represent the solutions for the system. And in order to compute this data structure, we make use of the underlying graphical structure. Importantly, once we compute this data structure, it turns out that we have a very good understanding of the whole solution set of the polynomial system. Once we compute this data structure, we understand very well all the solutions of the polynomial system. Because this data structure can be efficiently queried for interesting properties of the solution set. For instance, if you want to know how many solutions you have, you can query the data structure, and this query takes linear time. And there are many other queries that can be efficiently done. And importantly, we also show that there are many interesting families of polynomial systems that may look complicated in the sense that they have exponentially many solutions or exponentially many components, but yet can be represented in a very compact way by means of this data structure. I would like to point out that this data structure that we introduced, these Chordal networks, it's actually remarkably similar to a class of data structure that is using computer science that is known as binary decision diagrams. This data structure, binary decision diagrams, actually made many breakthroughs in several areas of computer science, for instance, formal verification or circuit design. And what we believe is that this new data structure that we developed might lead to a generalization of these binary decision diagrams to much more general classes of problems. And the reason is that binary decision diagrams are often restricted to problems that are discrete, particularly to problems where the variables are binary, 0 or 1. But this technique that we developed can be applied over any field, and in particular, it can be applied for continuous variables that may lie over any field. And also, we may be restricted now to nonlinear constraints. These techniques based on Chordal networks, we implemented them, and they are available in a package that is called Chordal, and that anyone can use. And this graph that you see here in the top, this figure on the top, it illustrates a Chordal network that was automatically computed by this software. We applied these algorithms to applications from various domains that you may see here in the bottom. Perhaps let me just mention that in one of those applications, namely vector addition systems, we obtain precisely the plot that I mentioned earlier. So for this specific application, what we observed is that Chordal networks perform extremely much better than state-of-the-art techniques. And this illustrates that it's possible to take advantage of graphical structure and to obtain significant improvements. So that's really all that I wanted to say about past work. In the future, I want to continue working in developing and analyzing scalable, provable optimization methods. And I have three domains here in which I would like to work in the future. One of these domains is non-convex optimization. Non-convex optimization methods are very widely used nowadays, particularly because of machine learning. Non-convex optimization methods are used every day in non-convex optimization. The problem is that despite the fact that these methods are so widely used and that they work so well, we still don't understand very well why is it that these methods work well. And in particular, we don't understand when is it that these methods are going to fail. In the future, I would like to develop a general theory that allows us to understand which classes of non-convex optimization problems can be solved efficiently. I would like to point out that there are a few problems, for instance, the Burer-Monteiro problems, which are non-convex, but yet we do understand why is it that they work. But these problems are very specific, and in the future, I really would like to find a general unifying theory that allows that covers many more applications. Another area where I would like to work is in convex optimization. In this talk, I mentioned that there are many useful applications in which semi-definite programming relaxations have been actually very powerful. For instance, in estimation problems such as rotation synchronization. Well, it turns out that there are classes of optimization problems that we know that are more general than semi-definite programs. One of these classes is, for instance, hyperbolic programs. We know that there are classes that are more general than semi-definite programs, but yet these more advanced classes still don't have many applications. So another area where I would like to work is to try to understand whether these more advanced techniques could lead us to some novel relaxations and some novel algorithms that significantly improves the ones that we are currently using. And finally, one more area where I would like to work, or where I would like to continue working, is in the study of polynomial systems. I mentioned at the end that polynomial systems have many applications, for instance, in power networks, but yet scalability remains an important issue. In my work, particularly with regard with Chordal networks, illustrates that it's possible to take advantage of problem structure and obtain significant computational improvements, particularly in the setting of symbolic computation. But yet our current techniques are not fast enough to tackle applications such as power networks. But I believe that this could be resolved if we start to rely on numerical methods for solving polynomial systems as opposed to symbolic ones. And the reason is that numerical methods don't have to pay the price that symbolic methods do, which is that they have to represent the solutions exactly. So I believe that numerical methods, that there's a lot of work to do regarding numerical methods. But also in the case of symbolic methods, I also believe that there's a lot to be done, particularly in the connection between Chordal networks and binary decision diagrams. And that's really all I wanted to talk about today. These are the references on which this talk has been based on. And thank you very much for your attention. I'm open to questions now.